Imagine you are planning the ultimate cosmic road trip through our solar system. Mars sounds like a solid choice, right? A long drive, but a familiar destination with plenty of rust and dust. But what if you wanted to backpack to Mercury, the second closest planet to Earth? You might logically think, hey, it's closer to the Sun. We just drop down, right? Must save a ton of gas. Wrong. Completely, astronomically wrong. In reality, sending a probe to Mercury is dozens of times harder and insanely more energy expensive than visiting Mars. In fact, simply shooting a spacecraft entirely out of the solar system past Pluto is often easier than paying a visit to our tiny, sun-baked neighbor. Sounds completely counterintuitive, doesn't it? But the universe doesn't really care about human intuition. To understand this bizarre paradox, we need to throw away the flat, 2D map of the solar system you saw in school. Out here, distance isn't your main problem. The real currency of space travel is energy. Right now, just standing on Earth, you are hurtling around the Sun at a blistering 67,000 miles per hour. Think of Earth as a high-speed bus on a cosmic highway. If you want to jump out and reach Mars in the outer lane, you just need to step on the gas a little bit to catch its wider, slower orbit. Easy enough. But if you want to visit Mercury in the inside lane, welcome to the Mercury orbital paradox. To get there, you don't step on the gas. You have to hit the brakes. Really, really hard. You have to bleed off a massive amount of your orbital speed just to start falling inward. And that aggressive reverse thrusting requires an astronomical amount of rocket fuel. Why? This is where the final boss of our solar system enters the chat. The Sun. It's not just a giant, friendly cosmic space heater keeping our planet warm. The Sun contains a staggering 99.86% of all the mass in the entire solar system. Everything else combined, every planet, moon, and asteroid, is basically just a cosmic rounding error. This incomprehensible mass bends the fabric of space-time, creating an incredibly deep gravity well. Imagine the solar system as a gigantic, slippery cosmic funnel with a massive glowing sun sitting right at the terrifying bottom. Earth is comfortably cruising around the safe upper rim of this funnel, while little Mercury is zipping around way down deep, dangerously close to the fiery center. To reach it, you have to steer your ship off the safe ledge and dive straight down into that pit. But here's the kicker. In space, falling literally means accelerating. The deeper you drop into the sun's gravity well, the harder and faster it pulls you. Your spacecraft starts picking up a terrifying, completely unmanageable amount of speed. It's basically like riding a roller coaster with no brakes, heading straight into a blast furnace. If you just let gravity do the work and free fall towards Mercury's orbit, by the time you get there, you'll be moving way too fast. And to make matters worse, Mercury's own gravity is incredibly weak. It's literally like trying to catch a speeding bullet with a butterfly net. You'll just blow right past it, waving goodbye to your solar vacation plans. And what exactly is waiting for you just past Mercury? Yep, a head-on collision with the ultimate nuclear reactor. Poof! You are now a very expensive, colorful cloud of cosmic dust. So, to avoid becoming solar barbecue, and actually successfully stop at Mercury, you have to constantly fight the sun's gravity the entire way down. You must point your engines forward and blast them continuously, which leads us to a massive problem. Here is the fundamental, hair-pulling curse of space travel. Rocket fuel is incredibly heavy. To carry the massive amount of fuel you need to brake at Mercury, you have to lift all that fuel off Earth first. But wait, now your rocket is heavier, which means you need even more fuel just to lift the extra fuel. Welcome to the cold, unforgiving tyranny of the Tsiolkovsky rocket equation. It's a vicious mathematical loop that aggressively punishes you for every single extra pound you add. When scientists crunch the numbers for a direct flight to Mercury, the delta V, the total change in velocity required, is so ridiculously high that building a conventional rocket for it is practically impossible. If we actually tried to build a rocket that carried enough fuel to fly straight to Mercury and slam the brakes, it wouldn't just be the size of the mighty Saturn V that took us to the moon. It would need to be roughly the size of the Great Pyramid of Giza. Actually, scratch that. Try 500 pyramids. Imagine an engineering monstrosity so unbelievably heavy that its sheer weight would crush its own launch pad into a fine powder. And even if you could build it, lighting the engines would probably just vaporize the surrounding state without lifting off an inch. So, brute forcing our way to Mercury with a giant gas tank is completely off the table. For a long time, this paradox made reaching the innermost planet seem like an impossible pipe dream. But human engineers aren't exactly known for giving up. If we can't bring enough energy with us, instead of stubbornly bringing all that energy with us, what if we just stole it? Enter the gravity assist maneuver, or in Mercury's case, the gravity brake. By flying incredibly close to a planet like Earth or Venus at a very specific angle, a spacecraft can essentially dump a massive chunk of its kinetic energy directly onto the planet. Because planets are huge, this speeds Venus up by an unnoticeable, microscopic fraction of a millimeter, but the tiny spacecraft slows down massively, completely for free, without burning a single drop of fuel. This graceful robbery drops the probe further down the sun's gravity funnel safely. But doing it once isn't enough. You have to do it over and over and over again, creating a flight path that looks less like a highway and more like a toddler's crayon scribble. This is exactly how NASA's Messenger and the joint European-Japanese Bepi-Colombo missions actually did it. They had to execute an outrageously complex game of cosmic billiards, bouncing repeatedly between Earth, Venus, and Mercury itself, slowly bleeding off momentum. But this brilliant fuel-saving hack comes with a brutal, unavoidable price tag: time. Because of all these dizzying orbital loops, a trip to our planetary next-door neighbor takes roughly 7 grueling years to complete. 7 long years later, you finally arrive. You unbuckle your seatbelt, stretch your legs, and look out the window. But don't unpack your cosmic beach towel just yet, because Mercury is an absolute nightmare of a world. On the day side, directly facing our final boss, temperatures skyrocket to over 800 degrees Fahrenheit. That is hot enough to literally melt lead, and definitely hot enough to turn your ship into a molten puddle of regret. But wait, there's a plot twist. Mercury has virtually no atmosphere to trap all that intense heat. So if you step over into the night side, the temperature immediately plummets to negative 290 degrees. You go from a pizza oven to a deep freezer in the blink of an eye, and the days here are bizarrely long. A single day on Mercury actually lasts longer than its entire year. Add in the fact that the sun is constantly blasting the surface with relentless, deadly solar radiation, and you quickly realize why this place isn't exactly the galaxy's top tourist destination. So, after spending billions of dollars and 7 years of complex orbital acrobatics to get to this hellscape, why do scientists even bother? Why go through all this trouble for a scorched, dead rock? Because Mercury is hiding some of the most mind-blowing secrets in the solar system. In the deep, permanently shadowed craters at its poles, where the sun has never shined for billions of years, NASA probes discovered something impossible: massive glaciers of solid water ice. Yes, ice, right next to the sun. Finding solid water ice on a planet that can literally melt lead is the ultimate cosmic irony. It turns out, Mercury isn't just a burned-out, boring cinder. It's a pristine, untouched time capsule, preserving the ancient, violent history of how our solar system formed, locked safely away in a deep freeze. The Mercury paradox teaches us a profound, humbling lesson about the nature of space exploration. The universe really doesn't care about what looks close on a human-made map. Out here, distance isn't measured in miles or kilometers. It's measured in energy, delta V, and pure human patience. It took the brightest minds on Earth playing a 7-year-long game of 4D orbital chess just to gently park a fragile metal box next to a boiling rock. And yet, we did it. Not because it was easy, but because we are fundamentally curious creatures. We look at a completely hostile, terrifying, unlivable hellscape, and we say, I want to poke it with a stick and see exactly what it's made of. The sheer audacity of engineering required to reach Mercury is a testament to human stubbornness. We literally stole momentum from giant planets to achieve the mathematically impossible. So the next time you look up at the twilight sky and see that tiny flickering dot hovering dangerously close to the sun, remember that sometimes the hardest places to reach are the ones right in our own cosmic backyard. If this deep dive into orbital mechanics melted your brain in a good way, you'd probably love exploring the rest of our cosmic neighborhood. And the absolute best way to support our journey across the universe is by checking out our official shop. Grab your very own squishy Earth, or maybe a slightly burnt Mercury, and write down your own crazy space theories. Every purchase goes directly into funding these videos, paying our amazing team of artists, animators, and researchers. If you can't buy anything right now, simply hitting that subscribe button and liking the video is a massive help. Don't forget to click the notification bell too, or else the YouTube algorithm might just toss our next video right into the sun. A huge shout out to our fantastic Patreon supporters who keep this channel alive. You guys are the real gravity holding us together. As always, thank you so much for watching, and we will catch you in the next cosmic adventure.